Okay, so example two was a step into the direction of, hey, we can figure out discontinuities even if we don't see the graph based off of what we know and what we've seen with limits and equations and function equations, right? Example three now says, well, what if that equation is a piecewise function? Well, before we even begin, I want you to consider the four pieces that we're given. We're given a linear part, straight line. We're given a quadratic. We're given another linear, and we're given another linear. So each of these pieces by themselves never has discontinuous behavior, right? A line will go on forever. 2x minus 1 goes on forever. It's connected. 3x plus 2 is connected for it. All the linear functions are connected, and the quadratic one is as well. So if there's going to be an issue of discontinuity, it's going to be where the line stops and the quadratic begins, right? So either they're going to go towards the same place or they're not. And so what we're going to do is we're going to check at all of the x values where one piece stops and the other one begins. We're going to check each of those to see if they actually connect, or if there's a gap, there's a jump discontinuity, or maybe there's a hole because they're both going towards the same place, but there's no y value defined there. So we're going to do this one at a time. We're going to look at this x value first. At x equals -2, that's where the first piece stops and the second one begins. There you go. I was trying to erase it and it wouldn't erase. So at x equals 2. So we're going to say, what is the limit as x approaches -2 of 2x minus 1? And we're going to say, what is the limit as x approaches 2 from the right side? And we're going to use x squared minus 9 because we want to see what kind of values we get. I'm sorry, we're approaching -2, not +2. So this should be approaching -2 from the right. X approaching -2 from the right, and x approaching -2 from the left. So I'm going to do direct substitution. If you substitute -2 in here, you're going to get -5. And if you substitute -2 in here, -2 squared is -2 times -2, that's +4, minus 9 is -5. Oh, well, they're going towards the same y value. So the limit exists, right? Now, is there an actual y value there? Is there an actual point, or is it going to be a hole? Well, that's when we can check. Is there an equal line? Because an equal line means this equation is going to give us the answer of the actual y value point at x equals -2. And there is. And we're going to use that formula. And we're going to get -5. So what we just saw is as we're coming from the left side, it's going towards -5. As we're coming from the right side, it's going towards -5. And then this symbol tells us, oh, this formula is going to tell us what the y value is at -5. I'm sorry, at x equals -2, which is -5. So there is no discontinuity there. Why? I'm going to say there's no discontinuity because the limit exists and it equals the function value. The limit exists, the function value exists, the actual y value when x equals -2, there is a y value, and they're the same. You'd be surprised how on the exam it doesn't always happen, right? Because they're trying to see if you really understand what's going on and are testing everything. So I'm going to look at the next x value. So the second piece stops at 1. The third piece starts at 1. So I'm going to say at x, I'll write it down here, at x equals 1. Once again, I'm going to take the limit as x approaches 1 from the left of this function. And because I'm going from the left side, we're going to use x squared minus 9. And I'm going to find the limit as x approaches 1 from the right side of this function. And because we're coming from the right side, I'm going to use 3x plus 2. We substitute 1. 1 goes in there. 1 squared is 1 minus 9. Well, that's going to give us negative 8. I substitute 1. 3 times 1 is 3 plus 1. Well, that's going to equal 5. What does this tell us? This tells us that from the left side, the second piece is going towards negative 8. But the right side, or the third piece from the right side, is going towards positive 5. And they're not going towards the same place. So not only does the limit does not exist, it doesn't exist because there's a jump in the graph. And so this is a non-removable discontinuity, or a jump discontinuity, non-removable or a jump discontinuity. There's a break in the graph. There's a break in the graph because on one side it's approaching one value, on the other side it's approaching another value. Does that make sense? So first endpoints that we checked, they were going towards the same place, and there was a y value there, and it matched. So everything was connected. The second one in purple, one side went one way, the other side went another way. There's a gap. That's a discontinuity. And so we checked the last one. Let me use, I don't know, let's use green, I guess. So now we're going to check the last one at x equals 3. So we're going to take the limit as x approaches 3 from the left. That'll be this equation. And we'll take the limit as x approaches 3 from the right, and that'll be this equation. And let's see what we get. When we substitute 3 in here, 3 times 3 is 9 plus 2, that's 11. When I substitute 3 in here, that's 4 times 3 is 12 minus 1, that's 11. So that means for the left side it's going towards 11, the right side it's going towards 11, so they're going towards the same place. So it can't be a jump discontinuity. I have to check, is there a y value there? And when I check the less than 3, well, it doesn't equal 3. And when I check the greater than 3, it doesn't equal 3. So this function is never defined at x equals 3, and therefore there's a hole in the graph. There's a deleted point because this graph never tells me, or this function never tells me what the y value is. Which function do I use when x equals 3? I don't know, so it doesn't exist. Therefore, they're both going towards the same place, but there's a missing point there. We're going to say that there's a removable discontinuity or a point discontinuity at x equals 3. So this is the destination that we're looking at. So because each piece by itself didn't have issues, lines don't have issues, quadratics, they're always connected. We checked the places where one piece stops and the other one begins, because either they're both going to go to the same place and there's actually a point there, or they're both going to go to the same place but there isn't a point there, or they're not even going to the same place. And those are the three situations that we saw with these three endpoints. That's how we can check for continuity, even if we don't have a picture of the graph.